Jerusalem. And I especially have a great pleasure to be in a conference in honor of Ilya Rips. If in the conference for Avinoam we said that Avinoam is the father of group theory in Israel, then Ilya is the father of combinatorial group theory in Israel. And I guess everyone in this audience and everyone in the area, in the world, know how great Ilya is as a mathematician, but maybe not everyone knows how generous and kind person he is. And sometimes you even have to save him from his generosity and goodness. I remember in the early days that once I mentioned to him that I have a problem with reading a Serre book, Trees, because at that time it was only in French, and it was not, it has not been translated yet to English. And Ilya said, I have it in Russian, I can translate it to you. If I would not stop him, he would sit all night and will translate the whole book just because I have to read it, because for Ilya it was clear, he has the book, he has the knowledge in Russian, in mathematics, he can translate, and I need it. So he should need it. Then he should do it. And so many times he's so nice and kind, which actually makes him completely useless as a referee, because Ilya cannot say any bad word on anything, and in particular he cannot say that a paper is not good enough or something. No, everything is good, everything is there. So in this sense is really very. Okay, I really wanted to take the opportunity to talk here in such an important combinatorial group theory conference on something which is not really combinatorial group theory, but it's a combinatorial group theory for profinite groups. In the early days, like 30 years ago, I had the ambition of developing it systematically. I even wrote a paper with that title, Combinatorial Group Theory for Propi Groups, and I planned that this will be a first in a series to continue. But somehow I was attracted to many other things, and I have not really continued this in a systematic way. And I thought for this conference to rethink, well, quite a lot has happened in these 30 years, and I want to give some kind of survey of what is known and suggest various problems. Because you see, in principle, one can and should do everything which we study in the discrete category also in the profinite category. Sometimes, well, both. I will talk about both profinite and propi, and they are different. In fact, I basically prepared 3 chapters, but eventually when I prepared it, I realized that maybe I will not be able to talk about all of them. And the last chapter, I called it Wild or Tame. Namely, in a propi, I think there is a tame theory that maybe can be controlled. The profinite is but even this I'm not completely sure, and I will maybe present a few test cases for this type of problem. Just to mention that, I mean, from a kind of a logical point of view, for example, let's just see a difference between the discrete category and the discrete and the profinite category. For this audience, I don't have to say that groups which are elementary equivalent are not necessarily isomorphic, right? We all know the famous theorem of Tzlil about 3 groups which have equivalent theory, elementary theory, but they are not equivalent, but they are not isomorphic. The free group on 2 generators and the free group on 3 generators are not isomorphic, but they have the same elementary theory. For profinite groups, Moshe Yarden and I proved that two finitely generated profinite groups have equivalent first order language if and only if they are isomorphic. Our work is not so difficult, but we used very deep work of Nikolov and Segal, which is based on the classification of finite simple groups in a serious way. So altogether, it's sometimes you need a lot of machinery in order to prove results like that. So sometimes the theory can be completely different than the discrete one, and sometimes it's similar one. And part of the game is really to analyze and understand when things are the same and when things are similar.
When you say they have the same elementary theory, you mean
just as group, right. Of course, you can study profinite. Maybe it's more natural to study it in a different context. And I mentioned this just kind of a quick results, which shows the difference. But from now on, when I will talk about in the category of profinite, I will talk when I say a subgroup, I always mean a closed subgroup, etc. within the category. So I want to divide my talk into 3 chapters. The one will be free groups. And the first one, then presentations, and then I will talk about wild or tame, and I'll try to present. So we all know, let's see if we can keep the discrete. I wish I have color, so maybe then I can, if I will, oh yeah, there are color. So I will, maybe let's keep, I don't know, let's say the yellow will be for the discrete category. So in the discrete category, we know the Nielsen-Schreier theorem, right? Every subgroup of free is free. By the way, to avoid various set theoretic issues, I concentrate all the time on finitely generated groups. Okay, if I'll talk about finitely generated free group, etc., you can extend it sometimes it's problematic, but I don't want to talk about that. And then if, say, H is a subgroup of Fn, so Fn is the free group on n generator of, say, index R, then by part 1 it's free, but we know that H is isomorphic to Fl, where L is equal R times n minus 1 plus 1, right? All this is well known. So if we compare it to the, so this is the discrete. What about profinite? In the profinite category, so first of all, let's recall what we mean by a free profinite group. So a free object is a free object in the category, namely, it satisfies the universal condition. You have a set, X is a set, and the free object, f of x, is the one such for, we have an inclusion of x to f of x, and every map from x to another object in the category can be completed uniquely to a map from the free object to G. In this case of profinite, it's very easy to get the free object. You start with the free group Fn, and you simply take its profinite completion, which is the inverse limit of Fn over n, where n runs over all the normal subgroup of Fn of finite index. This is the so-called profinite completion, and this is the free object in the category. This is the free object in the category of profinite group. Now, in the profinite group, part 1 is not true. Like subgroups of free groups are not necessarily free, and that's kind of an easy because in a profinite group, there is a Silo theory, and you can take, for example, the P-Silo subgroup of the free profinite group. Well, that's a counterexample, but it's not quite, because the P-Silo subgroup of the free profinite group is the free pro-P group. then you might say that this is not really a counterexample. But in fact, a free profinite group contains every projective profinite group. Projective means a projective object in the category. Now, in the category of discrete groups, the only projective groups are the free groups. But in the category of profinite groups, there are many. Every projective, and you can imagine what does it mean a projective group. Projective from the categorical point of view, every projected group is a subgroup, and the profinite G is projective. That's a theorem now, what I'm saying. It's not completely trivial. It's projective if and only if each P silo of it is free. So for example, if we will take the product of the free is free pro P. So, but now I can take a product of free pro P groups on different number of generators. For example, I will take F, I don't know how to denote it, say F P P, where this one is, say, the free pro P on P generators. Why not? And then this is a projective group. This will be a subgroup of a free profinite group, and it's not free in any sense, in any reasonable sense of the word. What? It is. It is. Okay. This one is not. But okay. If you want, okay. So take one of. So do it. Take one of them to be two generators. Okay. So divide the primes into two and take one of them. Right. No, right, because usually it's not, but because I say I concentrate that, as you know, I insist that I will continue. My word is my mashgiach kashrut, you know, that whatever I promise I'll continue. But even if we can overcome that. Okay, so we can get plenty of them. That's that. But two is true. Namely, this part about finite index subgroup is true in the profinite category. Finite index subgroups behave just the same, and in fact the proof is very easy. You deduce it from this result by standard argument of profinite completion. Is just kind of almost general nonsense to prove part two. There is a cute result which I want to mention. It was proved in slightly different forms, but by Melnikov on one end, and so it's opportunity to mention because Melnikov just passed away a few months ago, and in a joint paper of Lou van den Driesch and myself, something like 30 years ago, kind of surprising results in this context. We prove the following. If you take a normal subgroup of Fn hat, then it's also not necessarily free. If you take a normal subgroup. Sometimes it's free and sometimes it's not. But if K is a finite index in N, but not equal to N, take a normal subgroup of the free profinite group and then take a subgroup of finite index, any finite index which is not 1. Take a proper subgroup in a normal subgroup, then it is always free. If K is a finite index in N, but not N, then K is free. Sometimes N is also free. In which case, finite index subgroup are free, that's easy. But even if N is not free, which is possible, for example, take the free profinite group and map it onto the free pro-solvable group, then the kernel has no abelian quotient, so it cannot be free. But if you take a proper subgroup by something, by any index, then it's already free. That's kind of a slightly surprising result, which has some cute application to Galois theory, which I will not talk. But let me pass right away to the propy category. In the propy category, everything is true. So this is exactly what more or less Ilya jumped over and said. 1 and 2 are both true, namely every subgroup of a free propy group is free, and of course the second part is also true. Now, so this is a much nicer category, and we can expect that in a propy maybe we can go ahead and prove various of the other results which are known for subgroups of free groups. So let's recall few of these results. For example, Marshall-Hall theorem. Marshall-Hall in the discrete category proved that every finitely generated subgroup is a free factor. So let's call it 3. Is a free factor of a finite index subgroup. And this is also true in the propy category. This is something which I also proved in that paper 30 years ago. Moreover, there is another theorem, a quite well-known theorem by Hobson, which says that if H and K finitely generated subgroups, then H intersection K is finitely generated. This is a property which usually not true in groups, that if you take two finitely generated groups, there is no reason that their intersection will be finitely generated. This is the case for free groups, and Hobson proved this with some quantitative bound. He proved it that the D is always the number of generators. That the D of the intersection is at most 2dh dk minus dh minus dk. Then, in a famous work of Hannah Neumann, she improved it. So this is Hannah Neumann, improved this to dh intersection k minus 1 is at most 2 dh minus 1 times dk minus 1. And then she made a conjecture, which was a famous conjecture for a good number of years, that one can omit the two. This is the so-called Hannah Neumann conjecture, that you can omit the two, and if you omit the two, then this is best possible. You can get examples like that if you take two finite index subgroups in the free group and two generators, which are kind of disjoint in the probability sense. You can see that this is the best possible, and this is the Hannah Neumann conjecture. Now, this conjecture of Hannah Neumann was proved recently by Yoel Friedman on one end and by what? Igor Minenko on the other end. Now, what's the situation in the propy? So here is an interesting story, because I mean, the results of Hobson, I proved that many years ago without any quantitative estimate. In principle, I could not get because the method did not give you I'm stressing this point because I'm calling this combinatorial group theory for Propy groups, but there is no combinatorics really. Somehow it's you cannot really do the combinatorics because you don't have the kind of thing that Ilya likes to do, all these diagrams and all these words or the finite graphs, because words in the generators are not finite. You know, they are kind of Propy words. You can get some form of them, but they be like an infinite type of word. Indeed, the intersection. So Hobson theorem is. So I prove Hobson theorems, but without a bound. But without any bound. And some of the method does not give you any bound. It's not like a bad bound. It's a method which cannot give you any bound. But there are big news now, and that's maybe, in a way, that's what's caused me to talk about that. Only a few weeks ago, Andre Chaikin proved a wonderful paper, which I have to admit that I have not digested yet. But Andre Chaikin proved Hannah Neumann result for Propy groups.
With the two or without?
What?
With the two or without? The two is not present?
Without the two. The conjecture, Hannah Neumann conjecture, sorry. Yeah, Hannah Neumann conjecture, without the two, yeah. And moreover, he got a completely different method of proof than mine and the previous proofs, and he can give also a new proof to the discrete case, which are not completely the same, but somehow the same spirit. So that's a very interesting paper that should be understood by some of the people here, which I call them to be in this talk. because this is really seems like to be like a new ingredients which come up to the. That's why I really expect. I hope that some of my students will study this paper and will explain me. That's my method this day to learn. Before we'll go to the second chapter about presentation, I want to mention another work which has an interesting history in this context, and this is the following theorem of Serre, this is an interesting example because usually you start with the discrete and then, you try to do profinite and Propy. But this theorem the history went the other way around. Serre proved it first for Propy. And the theorem is the following: if G is a torsion-free, virtually free group, I mean everything finitely generated today, a virtually free group, then G is free. Namely, if you have a torsion-free subgroup which contains a free subgroup of finite index, then the big group is also free. Serre proved it, virtually, if G is a Propy, that's what Serre proved. Propy group, which is virtually free Propy group, then G is a free Propy group in the category Propy group. He proved it using cohomological methods, and then he made the conjecture that this is true also in the discrete category, and this took few years, and then Stalling proved it in the discrete category. What?
Yellow choke.
Thank you. Yellow for the discrete. Right? What? Yeah. So it's also true in the discrete. Interestingly enough, and maybe not so surprising, but it was an open problem for a number of years. Moshe Yarden was kind of pushing the question: what about the profinite till Danny Aran gave a counterexample, not true for profinite. There is a counterexample in the profinite category. So you see again, somehow not always things are moving in the category. Okay.
Hall and Hausen results on the profinite case.
About what?
Hall and Hausen results on the
Actually a good question. I don't think I ever really pin it down seriously. I'm sure they're not true, but okay, students, work for you. I mean, that's never been cleared up, but that might be a good thesis work to do, to work on it, to show. I'm sure they're not true, but one should construct counterexamples. What? What is 3? Marshall all. For profinite.
Yeah.
Because.
Just take an element in the maximal propi kernel or the prosolvable kernel, like you said before.
And then it cannot be. Is it clear?
More or less, I think.
Okay, and I think also option is not true because you can get this. Well, yeah, okay, we have to think about that.
What about the analog cell theorem for the prosolvable piece?
I have the feeling that Aran, that Aran counterexample can be made prosolvable, but again, students, think about that. You see, there might be problems to think about. To go back to Aran, yeah, I think that the example of Aran was like that. I don't want to go because I have so much material that I don't want to stop, but I am pretty sure that this can be also in the prosolvable category. Okay, let me go to presentations by generators and relations. So chapter 2 will be presentations by generators and relations. And we'll see here there is something interesting, that the profinite category, even profinite works much better than the discrete in many aspects of it. So first of all, let's so this is chapter 2. Now, presentations by generators and relations. So just to make sure that we are on the same, if let's say if X is a set of size n, and then Fx hat, which is Fn hat, the free profinite group, if we take R is a subset of it, and let N be the normal closure of R, the closed normal closures. So it's the minimal closed normal subgroup containing R, the set R. Then we say that G, which is this F hat X over N, will write as a presentation X and R. And if we want to stress that this is as a profinite representation, maybe we'll put this hat. So this is a profinite presentation. But R, I want to stress, R does not have to be words in the standard sense, but it can be any set of elements from the set R. Now, an easy fact that if gamma X are discrete, I'll write gamma for discrete, then its profinite completion, you can take a presentation of gamma and just think of it now in the category of profinite group, and you will get a presentation for the profinite completion of gamma. Now, here is a question which I'm not sure what's the answer. I mean, I'm sure what's the answer, but I'm not sure I know to prove it. Here is a trivial question, or something which sounds trivial. We all know that there exist uncountably many finitely generated groups, and there are countably many finitely presented groups. Okay? Both results are not clear in the profinite or pro-p category. So for profinite, I know the answer, and for profinite, so maybe let's say according to our tradition, right? Discrete is what, Ilya? Discrete is yellow. Okay, so there exist uncountable many finitely generated discrete groups, and there exist only countably many, that's trivial, countably many finitely presented, namely those which are presented by finite number of gender of relation. But if we go to the profinite, okay, the second part is completely trivial. The first part, well, the kind of proof I know is by B.H. Neumann, who was the first one to prove it. But his proof used kind of a product of alternating groups. And so it's not work in the category of pro-p groups. It works in the category of profinite. And in the category of profinite, you can easily show that there are countably many. Now, what about in the category of profinite and finitely presented? You see, why there are only countably many finitely presented groups? Because I choose the free group is countable, and I choose finitely many elements of it, so this only countably many choice. But on the other hand, the free profinite group is uncountable. So if I choose finitely many words, I potentially I can have uncountably many, but the question is, are they isomorphic or not? So I know to prove that there are uncountably many profinite, but I don't know to prove so profinite was white was profinite or pink? Well, it was supposed to be pink. I think it just became okay, so profinite, there exist uncountably many finitely presented even, and therefore also finitely presented profinite groups. Actually, the way I know to do it is not completely trivial. I never wrote it down, but it's based on something which I wrote. Projective. I proved once that projective groups are always finitely presented, and it will also come up in something which I'll tell you later on. And you can see that there are uncountably many projective groups. For example, in what I told you before, but that's not really a trivial result, though I think it should be somehow proved probably by simpler method. But I really don't know what's the answer for pro-p. I'm sure that there are uncountably many finitely presented pro-p, but I don't know to prove it. I'll talk about that. That's very interesting. I'll get to that problem. That's something I want to present as a problem, but I don't think that will help you for that question. But yeah, I will come to that. Okay. But so this is kind of a basic problem about finitely presented. But let me say a little bit more about the issue of presentation. About discrete groups, there are various questions if you even fix the group and you ask about possible presentations of it. I want to stress that from view, the profinite theory or the pro-P theory are much easier than the discrete theory, namely, here is the fact. A profinite or pro-P group is an essentially unique presentation. There are not, what I mean by that is that if F is one way to say it, if F mod N1, like F hat, like profinite, is isomorphic to F over N2, namely the group G as a presentation as a quotient of the free group by two normal subgroups, then there exists alpha in the automorphism group of F such that alpha N1 is equal to N2. So now this was kind of a subject which really promoted in the 50s, I think, by B.H. Neumann about discrete groups, how many different presentations they have. If you take this, you consider this as the same presentation in a natural way. And then gradually people show that there are very different presentations. I think, Malden, you have a famous paper about that, no? It's not you who have some, but even for finite groups, there can be finite groups with different presentations, such that are different in this sense. And on the other hand, the profinite category, there is essentially one. And even you can prove that if you take if you even change F, it's really the same. You take more generators. I don't have time to explain, but it's not difficult. Anyway, corollary of this is that the number of relation, the minimum, you see, if I take such a presentation for G, I can talk about the number of relation as the minimal number of generators of N as a normal subgroup. Now, if we look at the number of relation of G in a specific presentation, minus the number of generators of G, in the discrete category, this is not invariant of the group. It may depend on the presentation, but here is an invariant of the group. So depends only on G in the profinite category. And all this is not difficult to prove. It follows from an extension of Gashitz's lemma to the profinite category. An extension whose importance in the profinite category was, I think, was shown for the first time by Moshe Yarden. So in this sense, we see somehow that the profinite theory is kind of potentially better, but I want to show you even much more than that. You see, in the discrete category, it's usually very difficult to know what is a minimal number of relations needed to define a group. It's very difficult to get bound. I want to show you an exact formula for the number of relations of a finite, of a profinite group. Here is a theorem. This is something that I proved some number of years ago, which says the following: a G profinite then R of G, maybe I'll say R hat of G, as a profinite group, the number of relations of it as a profinite group is exactly equal to the following formula. It's the number of generators of G minus 1 plus the maximum over all primes and over all M. Now, what is M? M is all irreducible FPG modules. Like, you take all the finite, irreducible here must be finite. So all finite modules of G in characteristic P, and you calculate the following. You calculate the dimension of H2 of M. It's kind of a partial Euler characteristic, minus the dimension of H1 of GM, plus the dimension of H0 GM. Then you take, so you divide it by dim M. This is not necessarily an integer, so you take the smallest integers, which is bigger than this fraction. You do this over all prime, over all M, and that's what you get as exact number of relation. Let me show you a special case of that many of you should know, and this is the following. If G is pro-P, okay, if you do it in the pro-P category, then let's see what happens. Then, maybe let's say if G is pro-L, where L is some prime number, then if P is different than L, then H2 is 0, H1 is 0, H0 is usually 0 unless this is the trivial module. So let's assume for a minute that it's not the trivial module. And so all this is 0. So there is no contribution if P is different than L. The only contribution is when P is equal to L. If P is equal to L, the only irreducible, for a P group, the only irreducible module over Fp is the trivial module. And then what we got here is the dimension of H2 GM minus the dimension of H1. But the dimension of H1 in this case is equal to the number of generators of G. And this is equal 1. And dimension of M is 1. So this cancels this one as this, and this cancels this one. And then we get that in the case of a pro-L group, the number of relation is the dimension of H2 of G in the trivial module FL, which is a famous result, which I don't know, appeared probably first time in the book of Serre, Cohomology Galoisienne. And this is a generalization of that. For example, from here you can see, if you want, that a projective group is finitely presented. You can also deduce from here as a corollary that G is finitely presented, assuming it's finitely generated, right? If and only if there exists some constant C such that the dimension of H2 with coefficient in M for every P and every M is at most constant time dim M. So we have a very relatively simple cohomological condition to check if a group is finitely presented. Of course, I mean, I have to be careful here. Not always is so easy to compute this cohomology, but there is at least a method how to do something which is very much missing in the case of a discrete group. I want to stress. This is a 1 hour talk. Okay, so I still have some time. Okay, fine. I want. Maybe I will give you. I want to explain something. I mean, I'm not going to give the proof, but I want to give you the main, that you understand why we can do it in the profinite and we cannot do it in the. Let me say that will take 1 minute. Say line of proof for this theorem. Why this theorem is true? You see, we have G, which is F mod n. F is a free profinite group divided by n. And we have a set R in n generates in as a normal subgroup if and only if it generates it, again, as a normal subgroup, modulo, I'll write it like calligraphic M, which will be the intersection of all the maximal normal subgroup. Look at all the maximal normal subgroup of N, and look at the and M maximal normal in G. In N, sorry. And look at this intersection. Then it's easy to see that in order to generate, it's enough to generate it modulo all the intersection of all the maximals. That's true in the discrete category, and that's true in the profinite category. But in the discrete category, it gives you nothing, because this intersection is the trivial group of N. N is the free group. If you take the intersection of all the maximal normal subgroups in N, this is the identity, so you gain nothing. On the other hand, in the profinite category, as N is profinite, here is a very simple exercise. Just think about finite group. If you take, and the same is true for profinite. If you take in a finite group the intersection of all the maximal normal subgroups, and you look at your group modulo this intersection, then this is just a direct product of finite simple groups. Then N modulo this M is a product of many finite simple groups. Many, and each one will appear infinitely many times, but doesn't matter. Many finite simple groups. Now, write this product, divide this product into the finite simple abelian group, and write N over M as A cross B, where here is the abelian, the finite simple abelian group, the cyclic group, and B is the non-abelian finite simple groups. And I need now to kill both of them as a normal subgroups, but it's trivial to kill this part. Why? Think about it. If you have a product of finite simple, non-abelian simple groups, and you ask, how do you kill it as a normal subgroup? You kill it by one element. Take an element which is non-trivial in every component, then its normal closure, it's elementary group theory, nothing. Its normal closure is everything. Right? I mean, it's not going to be a finite word. It's going to be a profinite element. But so all this you kill by one element. So basically you have to treat only the abelian case. The abelian case is very much related to the so-called relation module. And that's what brings cohomology into the game. The cohomology is exactly the way to understand how to treat abelian case. That's what brings the truth. And that's what makes the profinite category more amenable to this machinery, something which doesn't work in the discrete category. Okay? So, okay, but then, but now, as I said, I mean, that's nice, and in some cases you can really do, for example, as I said, if the group, we still have the formula? Or I erase the, no, yeah. For example, if the group G is projective, then we know that for projective groups, it's kind of by definition, they are of cohomological dimension 1, then H2 always vanish. This is always less or equal than this one. And then for the cohomology, then we can see that projective groups are always finitely presented. But usually if I give you a group to compute its cohomology, and to decide whether it's finitely presented or not, it's not so easy, and sometimes you need various technique. For example, let me illustrate. Look at the group SL, one of our favorite group, like SLNZP. the p-adic Lie group SLN over the p-adic integer. So for these groups to prove that they are finitely presented, one can really prove directly. One does not need cohomology. It's possible also by the cohomological method, but this is known. It's already in the book of, you go to a finite index propi subgroup, and you know that the standard techniques that a group is finitely presented if and only a finite index subgroup is finitely presented works also here. It has a powerful finite index subgroup, and powerful groups are always, propi groups are always finitely presented. But there was a question which was asked by Iftach Barnea long ago. What about SLN FP? Like these analytic groups in the characteristic P, yes, and then the technique does not work. And in fact, I don't know direct proof which uses this technology of the cohomology. Eventually, we managed to solve it by a completely different technique. I mention it because of the connection with discrete. So sometimes you go to the discrete, you look at the group gamma, which is SLN FP T, and if gamma, and assume, now this group gamma is finitely presented at least if n is greater or equal 4. Now for the case SL2 and SL3, you can also solve the problem by some trick which I will not mention, but let's take the kind of the generic case. And then you look at its profinite completion. If the group is finitely presented, then its profinite completion is finitely presented by the trivial remark I mentioned at the very beginning. But now we know by the affirmative solution in this case to the congruence property that this is equal to an infinite product of groups like that. So it's a product of something like that, but a product with more things like that. What?
The brackets there should be
Double, yes. Thank you. With more. Now, all these more are quotients of this group. So, the more is generated by finitely many elements because this is a finitely generated group. So, by adding some finitely many elements which are profinite relations, they are not any more discrete relation, I can kill this part. And I am left with this part, and they show that this part is finitely presented. So you use the results. So this is kind of an interesting method of proof because you go from the discrete to the profinite by using some results on arithmetic groups to prove finite presentation for profinite groups. There is now work in progress, which I'm working with Ina Korchagina and Bernard Remy. Generally, this simple idea to a more elaborate situation when you use Katz-Moody groups instead of the arithmetic groups. And we also get some bounds, better bounds, which make the number of relation independent of n, and etc. But this is too technical, which I don't want to go here. There is an interesting story. I want to take you to one of my favorite problems. This is actually my favorite open problem about this subject, and I'll tell you here an interesting story. So you remember I told you that if you start with a group, with a discrete group, and you take its profinite completion, then the same presentation serves as a presentation for the same group, for the profinite completion of that group. And this is very easy. Let's do it in the simplest trivial case of a finite group. Namely, let G be a finite group, and then I write XR as a discrete presentation. Then, of course, G hat, the profinite completion of a finite group, is equal to G. There is nothing to complete. It's already completed. And the same presentation serves for it in the profinite category. So what does it mean? It means that the number of relations needed to define G in the profinite category is always less or equal to the number of relations needed to define G in the discrete category. Right? And this is completely trivial. The big open problem is it ever a strict inequality? We don't know, even single case, open problem, is there a finite group with that you can present it in the profinite category by less relation than what you can present it in the discrete category.
What about the property case?
The same problem, yeah. It's also completely open.
So we know groups with equality, right?
I know groups with equality, right, that you cannot do better, yes. There are some groups which we know to prove. Basically, you see, the only technology which is known to give lower bound, it's very difficult to give lower bound on the number of relations. The only working method is using cohomology, H2. But if they work, they already give you for the R hat. And sometimes they are sharp. Namely, you see in a lower bound, and you know to present, and then you are done. But in all cases that you do it, that's the only method. And therefore, what we are really missing is a method which not through cohomology. Now there is a nice story here which led us to some work. Some number of years ago, there was an interesting conjecture of Latzi, Piber, and Avinoam Mann, and they conjectured that they wanted to count the number, because of problems in subgroup growth, what is the number of, the conjecture was that the number of finite groups G, such that the order of G is at most n, and the number of generators is at most d. And they wanted to prove that this is at most n to the constant dn for some absolute d log n, for some absolute constant c. And Avinoam made a reduction of this. He made a reduction of this problem to prove, he connected it with the theory of presentations of finite groups, and he made a reduction that this will be proved if you prove that for every finite simple group, R of G, the number of relation, is at most some constant log the size of G. And when he made this reduction, that this would imply this. It was known that this is true for most of the groups, but some groups were not known, and I think some of them is still not known, very few though. Now I made a little observation. I basically went over the proof of Avinoam, and I said in every place that he writes presentation, one can use profinite presentation instead, so it will be enough to prove it for this. Maybe this is not at all an improvement, because maybe R hat of G is always equal to R of G. This is the big open problem. But at least for this, we have a formula. Where is the formula? We have a formula, how much is this? In order to prove this, you have to go and to compute H2 for finite simple groups. In Hebrew we say, tzadikim melachtam na'aset bidei acherim. to translate in English, I say righteous people, their work is done for them by others. I discovered שאפילו זה נכון גם לרשעים. It's even true for the wicked one. Namely, so what it happens for me, that the work was done by somebody else. Namely, there was a work on the shelf, ready for 30 years ago, that somebody evaluated these are the easy one. That's not a problem to evaluate this one. It's always the H2. Somebody evaluated H2 of GM for finite simple group and gave exactly that bound that I needed. And therefore, I could say, good, so this works, and therefore, the Piberman conjecture is proved without this conjecture, without proving the original conjecture of Mann, only with the art. And the story goes like that. But when I look at these old papers, I saw there that there was a stronger conjecture.
But it involves the classification of finite simple?
What?
It involves the classification?
Of course.
Yes, you have to go over the
Everything involved. Right. When I look at this paper, there was a conjecture there that what they proved that the dimension of H2 is at most constant log G times the dimension of M. But the conjecture was that this is at most constant times the dimension of M. Assume this conjecture would be true, then this would mean that the number of relation is bounded, completely bounded. This looks to me very strange, but it was not my field, but I happened a few years ago to be at the Institute, Advanced Study, and my office was just next door to Bob Guralnik, who is a big expert on this cohomology. I probably would not bother with this conjecture if it would just be so convenient to tell him. And I told him, there is this conjecture, I saw it in one of the papers, and it cannot be true, because if this would be true, then we will have, for the finite simple groups, a profinite presentation with a bounded number of relations and AN, we all know the presentations for AN. By the Coxter, you can save relation, and there are many papers which bounding them. Anyway, and Avinoam conjectured you can do it in log G, but nobody conjectured it you can do it with a constant number of relations. So Guralnik went home and checked, and then he came back to me and said, oh, the conjecture must be true. I mean, by now, 30 years after, we know so much more that it's at least true for many, many simple groups. This looks strange, so I told him, oh, maybe even better now. Because it means that if these groups has a profinite presentation with a bounded number of relations, but clearly a group like Sn, the symmetric group, when n is going to infinity, cannot have a presentation with a bounded number of relations, then we will solve this problem. By the way, this problem, even though I'm presenting it now, in this language is a 50 years old problem, in a different language about relation modules. I mean, it was presented already in the 50s or 60s in a different language which I don't want to explain. But it's completely equivalent. So if somebody solved this is a long-standing problem. So I told him, wow, we can solve this by giving counterexample. So I got even more excited. So we started to work on it. And then we realized that what I assumed that it's impossible is not at all true. Why it is impossible to have Sn or An or other finite simple groups bounded by, presented by a bounded number of relations. Anyway, we ended up with working on it for a long time, writing like a few papers with Kasabov and Cantor, and eventually we basically proved that all finite simple groups, except of some cases which could not handle, a few cases, regroups, do have a finite presentation with a bounded number of relations, which was against all what I grew up with. Somehow I couldn't believe it's true, but my friends who know this work should know that it all come because I really wanted to solve this problem. It was a failure of solving this problem that took us to that. Oh, my time is over, so I should not. I'll just, I'm telling you stories instead. So, Ilya, so ask me a question about Igman group. So that I will be able to take the time of questions and to answer. You ask me about Igman group, right? Okay. So now in the questions time, so I will not go to the other. I'll just say something about Igman. There are famous results of Igman saying that a discrete group is recursively presented if and only if it is embedded into a finitely presented group. Now, in the Pro-P category, we have a very interesting situation. There is a famous group called the Nottingham group. This Nottingham group, there are two major results about it. One is by Misha Ershov, who proved that it is finitely presented. And the other one is by Rachel Kamina, who proved that every Pro-P group, countably based Pro-P group, can be embedded into it. So if Igman theorem would be correct in the category, it should say that in the Pro-P category, every Pro-P group is recursively enumerated. But you have to be very careful here, because what does it mean for a Pro-P group to be recursively enumerated? Even a finitely presented group is not necessarily recursively presented. Because the question is, what are the type of the relation? This relates to the problem I mentioned before. Are there, it's kind of clear, right, that there are only, Nati, you should say, right? I mean, the number of recursively things is only countable, of course. So if there are uncountably many finitely presented Pro-P groups, which I believe there are, though I don't know how to prove it, then there are many finitely presented groups are not recursively presented, because we have to be careful here. The words, now, one can try to develop a theory, what does it mean for an element of the free Pro-P group to be recursive elements. That's actually, there is, I think, a notion which is natural. And then maybe one can prove Igman theorem of this style. So I'll stop here, I think that's enough. Thank you.